video, I'm going to talk about exponential growth problems with population where the time period is not 1. When we do population problems for exponential growth, we use the formula y is equal to a times b to the x power. We have y is the final amount, we have a is the initial amount, we have b is the growth rate, and x is, importantly, the number of time periods that have passed by. Not the amount of time that has passed by, but the number of time periods that has passed by. Most of the time, what the value that we put in here is the time that has passed by, because our growth rate is being applied every 1 unit, usually every 1 year, because we're usually talking about years. But sometimes that's not the case. Like, for example, if I have the population of koalas in Australia doubles every 33 years, that growth rate of doubling is being applied every 33 units, not every 1 unit. So I need to keep that in mind when I'm doing this problem. For this problem, the population of koalas in Australia doubles every 33 years. I want to know if the population at the start of the study is 750, what's the population in 112 years? I'm using this formula, y is equal to a times b to the x power. I don't know what y is. I'm trying to figure out what the final population will be. I know the initial population is 750. I know my growth rate is 2 because I see the word doubles. So I know I'm multiplying by 2 each time period, and I need to find out how many time periods there are. If I let x be the number of time periods that have passed by, to find how many time periods have passed by in 112 years, I would say, well, 112 years, I'm going to divide that by what a time period is. A time period is, in this case, 33 years. So I'm dividing by 33. And when I do that, 112 divided by 33, I get 3.39 repeating. So I have y is equal to 750 times 2 to the 3.393939 ... And I do this in my calculator, so I do 2 raised to 3.393939. And then I multiply by 750, and I get that the population is 7,883. I'm going to round down, even though this is 0.8. I'm going to round down because this is a population problem, and I'm increasing. I can't have a part of a panda. So I round to the nearest whole number, not panda, koala. I keep doing that. These are koalas. So I have 7,883 koalas. For number 4, I have radium has a half-life of 1,620 years. I want to write the decay function for a 8 milligram sample. I know I'm also using y is equal to a times b to the x power, and I want to find what I'm going to plug in for this formula. So I know the a value is 8 milligrams. It's 8 to start. I know the growth rate is 1/2 because I have a half-life problem. And I know if I plug in the number, if I let x be the number of years that have passed by, I just need to divide x by the time period, which is 1,620. Then I can plug in any amount of years, and I will get what my final amount is if I plug in any amount of years for x. So that's a, this is my equation that I will use for a, and then for b, I'm just plugging in 76 for the amount of years that have passed by. So I have y is equal to 8 times 1/2. I'm going to do 76 divided by 1,620 to find the number of time periods that have passed by in 76 years. And I get y is equal to 8 times 1/2 to the 0.0469 power. And when I do that, 0.5 to this times 8, I get 7.744 milligrams. And that's how I do it.